Hi, there's another lesson here for you on the Poisson distribution, and we're going to do what's called modeling with the Poisson distribution. And basically that means we look at real life examples and we try to see whether or not it's appropriate to use the Poisson distribution to do it. Now we've already seen, for instance, this formula in our PowerPoint 3A.1. We saw this formula or a version very similar to it, and that formula basically lets us calculate the Poisson distribution probabilities, probability x equals x, and so on and so on. And we've seen what all these things are before. Now, we also saw that on this class whiz calculator, or similar calculators which also have the Poisson distribution built into it, you can calculate them yourself. And these are two pretty graphs which are meant to be Poisson distributions. But as far as we're concerned, we're going to consider whether or not it's appropriate to use the Poisson distribution. Now I've got a little starter for you first of all. Now this starter is number of cases of a rare disease in a number of small towns. So lots and lots of towns and how many cases of these there are. Now in my first exercise, 3A.1 on the Poisson distribution, I did say these are very often considered to be rare events. So it's quite interesting that it says rare disease. And what's it want? It wants the mean and the variance. Now I can type these into my calculator. You might recall you at GCSE type questions, you did this x times f, where x is the number of cases. And you could do that similar here, or you could just go, I'm going to go into my calculator, which is menu. I'll turn it on now. Menu, and on this calculator it's menu 6. And but on different calculators, on another cashier I've got here, it says menu 2. So you press the stat, and you want 1 var. So what basically you press on the class whiz, you press menu 6, and then you press the stat option, which is 1 var. So we want the 1 var, one variable if you like. And my calculator is set up already with the frequency column set into it. If yours is not, you might need to use the shift setup. So shift setup lets you put the frequencies in. If you haven't got that already set up, you might want to just go back to basics and do 0 times 71 is 0, 1 times 23 is 23, 2 4s are 8, 3 2s are 6. And you might recall you basically add these up, these that matter, and then you divide by the number of small towns that there are. So you might want to do it that way instead. I'm going to chuck them into my calculator. So I'm going to type in 0, 1, 2, and 3 going down. And then the frequencies, I type in 71, 23, 4, and 2. I can ignore the 4 and more because it says none. So I think that's just there to cover their bases, that no one says, what if there was any more? So anyway, on this one, I now press the option button. On different calculators, you have to press shift and all clear shift and stat or something like this. So anyway, so on this calculator, I can then see, once I press the option button, I can see what the mean is, and I get 0.37. So mean equals 0.37. And likewise, when you see it, you can also see the standard deviation, and the standard deviation is usually written with a sigma x. So if you've got that on your calculator, you can see it. It will say sigma x because it does want standard deviation. Oh, it wants the variance. Now you can also see sigma x squared, I think. So different calculators work in different ways. So I'll just write it as sigma x squared. But you might find that yours does that. So 0.6581, for instance, times 0.6581. If I was to do it, it's not exact, but yeah, it's 0.43-ish. And you might find in your calculator it says sigma x squared equals 0.433. That is the variance. So you do need to be able to find these things for what we're doing today, which is why I've included this starter. It's useful to be able to do this. Anyway, by the way, if you'd done it like this instead and you add these up, I'm going to add them up now. I reckon they get 37. And if you add those up all together, I think you get 100. So if you like, sigma f is 100. And that's why x bar is 37 divided by 100, which is 0.37, which is, of course, the answer we got over here. Now, getting the variance out of that is much harder. That's why I personally cheated and just quite liked just typing them in. Anyway, there we go. backward problem, Poisson question. Now, these come about because sometimes we don't get told what the X is. We are asked to work out a probability. So let's see if this is one of those. The number of organic particles in 100 ml of pond water follows a Poisson distribution of mean 20. Okay then, so it looks like, so I'm going to write this is X is Poisson. It says mean 20. I'm expecting to get 20 of these in 100 ml of water. If the value, find the value. Oh, no, right, I see. This is not true. This is true for 100 milliliters of water, but it might not be 100 milliliters of water. That's what they're actually saying. The value of lambda, we want to find it. If the probability of there being no particles present is 0.09 and a bit. Well, this is definitely different. So X now is Poisson, and we don't know what it is. All we know is that the probability that X equals 0 equals 0.09, there being no particles. That's why I said 0 is 0.09. Now, I can ignore the two end zeros, but one thing you'll notice is that gives me a slight difficulty in as much that it's not obvious how you would do this because you don't have the lambda. Now, the easiest way to do it is to jump to the formula. Now, luckily, this formula is for X is equal to a number. So if it's 0 here, then I know it's e to the minus, I don't know my lambda, that's the whole point, e to the minus lambda times by lambda to the x. Now the x in this case is 0 over 0 factorial. Now that is very, very useful and deliberate that they were both zeros, because I can do that. If it was any other number, it would be quite complicated. But the answer, this probability equals 0.09. Now, if you type in 0 factorial, this bit equals 1. And you should recall that anything to the power of 0 is 1. So really, this tells me that e to the minus lambda equals 0.09, which is great because I can move the e onto the other side. I get minus lambda equals natural log of 0.09. I'm going to type that into my calculator because I have no idea what that is. The natural log of 0.09. Now I'm assuming it's a negative number, yes, because it was less than 1. So minus lambda is minus 2.408, which presumably means that lambda is 2.408. It's a bit more detail than I needed probably, but that's what I've got. So that is a backward question. We didn't know something about it. We didn't know the lambda. Because we didn't know the lambda, we couldn't use the cheaty button on our calculator, and we had to use the formula instead. Part B, it says the volume of water sampled is 0.09 again. Oh, right, because basically we want the volume of water with the same situation as before, the 0.09 bit. But we don't want just lambda now, we want the volume. Now, let's just write this down. When we had a mean in the original question, when it said when the mean was 20, that meant we had 100 mil. That's right. And now we've got a mean of, what is it, 2.408. And they're basically saying, what's the volume? This is the question. I think it's almost like similar shapes, or almost like scale factors. So I think the volume divided by the original volume, 100, is got to be equal. Now I did volume first, so I'm going to do 2.408 divided by the 20. And essentially, if I move that 100 over, it becomes 100 up there. And you'll notice 100 divided by 20 is 5. So it basically means initially I had 100 milliliters, and that gave me a mean of 20. Now I've got a smaller mean, so what's my amount of volume I've got? If you do 5 times 5, 2.4 is 12, so it must be 12 point something. 2.408 times 5 is 12.04. So that's how much water in my sample I think I must have. What are my answers? 2. Oh, it's gone off the bottom of the screen here. So 2.4 is right, and this is right as well. A modelling question, so very much different. A model is basically where we try to fit real data to a situation. Now, it is broadly known that injuries occur at a broadly constant rate. So this is a firm looking at how many people get injured at work, and obviously in 1 week, there was, in one particular week, we got 3 injuries. In 3 weeks, we got 2 injuries. In 17 weeks, we got 1 injury, and in 1 weeks, there were no injuries at all. So again, we would have to type this into our calculators. I'm going to go into that 1var stat mode again. So just doing it quickly, you can go into 1var stat mode as well, type in these numbers. Now they look, I'm not sure if they're the same numbers as we had right in the starter. Perhaps they are, perhaps they're not. Just in case, I'm going to type them in. 31, 17, 3 and 1. And I'm going to press that option var again because I've got the class whiz. And the mean, when I do this, it's the x bar, remember, and it says 0.5. Right, there you go. So I've got x bar equals 0.5. So that's the mean. And remember, I want the standard deviation. Well, technically, I want the squared version of that. So I'm going to do that as well. So again, you probably can see it on your screen, but just in case, I'm going to do, depending on which calculator you've got, I suppose. So sigma x is 0.693 on this calculator. 33, etc. So if I square that, I'm going to say squared, I get 0.4807. Now that's interesting because that is very, very, very close to this. It's not perfect. I mean, you can't expect it to be perfect. It's real data. Well, as real data as they've made up. So when would it be appropriate to use the Poisson distribution to model this data and then find the mean and variance? I think I've done part what probably should be called part B and part C here. I think I've done the mean bit first. I think that's 0.5 and this is 0.4807. What does this tell you? This tells me the Poisson is likely to be true. Now, what did part A say? It says what conditions would need to occur for this to be appropriate. And it does already say there's a broadly constant average rate. So I suppose we just need independent and random events. Remember that rule that we saw in the first PowerPoint on Poisson? So if we had independent and random events, knowing what we know, it tells us the Poisson is likely to be true. It's a good model. Okay, so use the calculated mean. Okay, so x is now Poisson. It said the mean was 0.5. Find the theoretical frequencies of the Poisson distribution. Now, look, to do this, I've actually got to work out some probabilities first. I need to work out the probability x equals 0, x equals 1, probability x equals 2, etc. I need to do it. I mean, I could go up to 4, I suppose. And I can type these into my calculator and get my calculator to work them out. Of course, I've now got the Poisson distribution. Probably best if you do this on the list function. So on the class whiz, I would recommend you type in menu. You type in 7. You press the down again. You press Poisson. Now we want exact probabilities. So I'm going to go Poisson PD. And I'm going to say for this first one, I'm going to say lambda is equal to 0.5 and my x value is equal to 0. And I'm going to type that in, but I'm going to do it for all of them. And I'm going to write them on the screen and I'll come back to you. You can do it as well. So I'm going to pause the video now. It'd be great if you could pause the video and see what you get as well. And here they are. These are my probabilities. I've typed all these in. I used the list function and I've got these. So 0.6065 for the first one, for instance. Now, look, bear in mind, these are probabilities. These are not theoretical frequencies. You get the frequency. You might remember, for instance, that the number of things you expect to happen on a probability question is n times by the probability. This might be a formula you've seen in the past. So based on the fact, how many there are set 31, there are 52 weeks in a year. So if I times all of these by 52, I should get my answers. I'm going to calculate those now. You can do the same. Pause the video now. And there are my answers. Notice, by the way, I wrote that wrong. So now hopefully that's right. 0.00158. I've times them all by 52 and I've got these answers to one decimal place. Now notice how accurate they are compared to the actual original numbers. They're not perfect, but they're pretty close. So this tells you the Poisson distribution really was a good fit for this set of data. that's what we want to do in class. Anyone who's got the textbook, you can welcome to have a look at those as well. Thank you very much. All the best.